Hello, everyone. In this video, we will look at another popular transfer learning architecture known as Inception. We will see what it is, explore its design choices, discuss its pros and cons, and finally compare and contrast it with the VGG architecture. So, let's begin. The Inception architecture was developed by researchers at UNC Chapel Hill, University of Michigan, and Google in 2014 and brought a significant shift in how convolutional networks were structured. The name Inception was inspired by the Network in Network paper by researchers from the National University of Singapore and a popular internet meme at that time. One of the key inspirations for the Inception design was the need to address the problem of how to make the models deeper and wider so as to increase performance without incurring a heavy computational or memory burden. This was because of the desire to increase the model's utility by incorporating it into mobile and edge devices. The core idea behind Inception is the use of what's known as the Inception module. This module includes convolution layers with different sized filters arranged in parallel, such as 1 by 1, 3 by 3, and 5 by 5. This configuration allowed the model to capture information at multiple scales. Furthermore, the introduction of 1 by 1 convolutions before the larger convolutions helped in reducing the dimensionality of the outputs, which helped in cutting down the computational requirements considerably. The outputs from these different scales were finally aggregated so that the next stage could extract features from different scales simultaneously. The architecture also includes a variation of the Inception module, which for this discussion we will call Inception plus plus module. The Inception plus plus module was designed as backpropagating gradients over a deep network can be tricky. So additional dense layers or classifiers were added to the Inception module in the middle layers of the network to create the Inception plus plus module. During training, the losses from these were weighted and added to the final loss. During inference, their output was ignored. This slide shows a simplified version of the Inception network. As can be seen, it starts with a few convolution batch norm and pooling layers, which we have combined together here in this module called Block A. After Block A, the Inception network really is just stacks of Inception and Inception plus plus modules stacked one after the other, with a few pooling layers in between to reduce feature map size. The 3 dots there at the end represent that this stacking of Inception and Inception plus plus modules continues for a while before the final dense layer. Pretty simple again, right? This modular design not only helps in adjusting to different feature scales, but also enhances the network's ability to capture complex patterns through depth and width. Let's now look at a few ideas proposed by the team in their research paper. One of the core ideas proposed by the team was of using different filter sizes. They confirmed that different filter sizes were indeed better at handling different scales in the image dataset as compared to a single filter size. Another important idea was the use of 1 by 1 convolution layers for dimensionality reduction. This removed computational constraints and allowed the architecture to go deeper and wider without significant performance penalty. These two were the core ideas that helped the Inception architecture to optimally manage model size and efficiency. Coming to pros and cons, while Inception is powerful, it does come with increased complexity, which can make it hard to train and optimize. Also, the deeper and wider network might potentially lead to overfitting if not properly regularized, or if training without sufficient data. Finally, let's compare this to another popular architecture, the VGG model. The VGG architecture adopts a more straightforward approach using multiple 3 by 3 convolution filters stacked on top of each other to increase depth. While VGG models are simpler and often easier to train due to their uniform structure, they typically require more computational resources. In contrast, Inception is designed to be more computationally efficient thanks to its varied convolutions and depth. In terms of performance, both architectures have shown great success, but Inception often leads in efficiency and adaptability to different image sizes and scales. VGG, while powerful, tends to be slower and more resource-intensive, particularly in deeper configurations. In summary, the Inception model, with its unique module-based design, introduced the computer vision community to concepts and ideas it had not seen or thought of before. The architecture represents a superior blend of efficiency and performance that caters well to the diverse needs of image recognition tasks. Comparatively, VGG offers simplicity and depth, which is excellent for many applications, but not as resource optimized as Inception. And that is all for this video on the Inception architecture. In the next video, we will see how to build an Inception model on real-world data using Python and TensorFlow. So, see you there.